Okay, grade 11s and 12s. So we're just kind of finishing up. We just have a few more lessons left. After this lesson, just two more. So we're just continuing on with solutions. What we'll have left is acids and bases. So today we're going to be talking about controlling how fast a solute will dissolve. So last week, the primary focus of the lesson was determining if something will dissolve. So, as a chemist, kind of analyzing two substances and saying this probably will dissolve in this or it probably won't. And that was based on things like temperature. Well, you'd have to know what's the temperature, what's the pressure, what's the polarity of it, and then what's the size of the molecule. Now, today's lesson is going to be kind of following that up and basically saying, okay, once you have determined that it will dissolve, okay, so you've kind of already done last lesson and you determined it will dissolve. Now we're going to kind of control, well, how fast or slow is it going to dissolve? So we're going to kind of, as chemists, we're going to be able to control how fast this thing will dissolve or how slow it will. And, we'll talk about some examples of why you'd want to be able to do that. Okay. So we're going to be primarily focusing just on solids into liquids today. So dissolving a solid into a liquid and then controlling how fast that happens. So if we know a solid is soluble, and that's kind of last week's lesson, okay? So an example of a solid that's soluble is NaCl, okay, in water. And again, because NaCl is ionic, okay, water's polar, the charges interact, so it'll dissolve. Now we can look at ways of, and this is the primary focus of this week's lesson, increasing and decreasing the rate of dissolving. Now, why would we care about this? Well, as chemists, okay, we are in charge of, when people produce products, basically kind of controlling the dissolving rates. So a couple examples would be, say if you look at the bottom left-hand picture, you're dissolving an antacid tablet. Well, you want to control how fast that tablet dissolves, okay? So if you're trying to make an antacid, you actually want to dissolve quite quickly. So when you drop this tablet in, you want it to dissolve into the water as fast as possible. So you're going to kind of go through your design of this tablet and kind of what we talk about today as to how you'd make sure that thing dissolves really, really fast. Now, conversely, if we look at, say, something like a pool, okay, and you're going to have chlorine tablets, you don't want them to dissolve within a matter of seconds or a matter of minutes. You actually want them to dissolve rather slowly, but for a prolonged period of time. So we're going to talk about how they do that. How do you control that this thing will dissolve slowly and not just rapidly dissolve once you drop it in there? Because if you did that, you would just make an extremely strong version of hydrochloric acid inside the pool, because you're dropping chlorine into water, makes hydrochloric acid, which make it super, super strong, would burn your skin, okay? We sometimes feel it if you open your eyes underneath the pool. That's hydrochloric acid burning your eyeballs. But if you dissolve this many pucks all at once, it would make an insanely strong solution. Okay, if you've ever shocked a pool, that's what you're doing. You're kind of making a super strong solution. That's why you pour it in as a liquid already. Okay, and then our last example is in medications. Okay, we make different types of medications, some that we want to dissolve really fast and some that we want to dissolve really, really slow. So a fast-acting one would be something like, say, a blood thinner or something that has to happen really, really quickly. So you want that medication to go into the stomach and then immediately dissolve. Other medications, like, say, a 12-hour aspirin or even like a 24-hour aspirin, why it can last so long is basically you slow down the way that it dissolves. And basically the pill, if it's a 24-hour, say, pain reliever, it will slowly dissolve in your stomach, slowly releasing that pain medication over a 24-hour period or a 12-hour period. Okay. So in several different products, we kind of want to be able to control this. So this is how chemists do that. Okay. So it can be a little bit confusing, last week's lesson and this week's lesson. So I just kind of want to clarify. Okay. Last week's lesson was this. Okay. If it will dissolve. And that was based on temperature, size of particle, pressure, and also polarity. I didn't add polarity in there. This week's lesson is basically saying, okay, we've already figured out that it will dissolve. Now we're going to talk about affecting the rate of dissolving, or how fast or slow it is. Now, a couple of them are the same. Okay, temperature is the same, but these two are different: agitation and surface area. Okay, so this is really going to be the three factors that control how fast something dissolves. So this is what we've done in class. Just something to think about. If you wanted to dissolve all this salt into some water, what would you do? Okay, if you wanted to get this done as quickly as possible, just kind of thinking in your head of your prior knowledge, what would you do to get this salt dissolved as quick as fast as possible? Okay, so think of like how you would set this up. Now think of also all the details. Okay, now you can pause this video and kind of think about that, but I'm just going to keep on for time. All right, so just going back to this, how you would do it is, one, you'd want to have a lot of solvent. Okay, you'd want to have a lot of water. The more water you have, the faster it's going to dissolve. Okay, the other thing you'd want to do is you want to heat up the water, because when you heat up things, solids dissolve in liquids when the liquid is hotter. Okay, you'd also want to stir this. So as you put it in, you were going to stir it around. Okay. The other thing you'd want to do is you'd want to crush this up into a powder. Right now it's kind of in these small little crystals. If you want to dissolve it as fast as possible, you want to get it into a powder form, because that will dissolve it much faster. Now we're going to kind of go through, well, how did you know that? Then, well, it comes down to chemistry. So the three major effects on controlling whether a solid dissolves into a liquid at a certain rate, so how fast you're going to do it, is temperature, agitation, and particle size. Okay, and one of these is kind of something that we should already know about, temperature. Let's start with that. So for solids, okay, and we're talking about solids here. So for solids, the rate of dissolving is higher at higher temperatures. The hotter you can get the solvent, the faster our solid is going to dissolve in it. Okay? Now this is the reason. This is more important for the U's than the C's, but it's important for both of you guys to know. The reason why at higher temperatures is when temperatures increase, basically all the particles move faster. Okay, and they move bigger distances. So they're like flying around there. When you have a low temperature, the particles just move a lot slower. And they don't move as big a distance. They don't have as much energy. Well, when you drop something into this scenario over here, all these, and you can think of these as water particles, start smashing into the solid particles and, causing them to break up and dissolve really, really quickly. Over here with lower temperatures, since the particles aren't moving as fast, they can't really separate that solid as quickly. Okay, now the next one that has a big effect is agitation. So if you stir something, it increases the rate of dissolving. So as you stir, that's one of the reasons why we do stir things, is basically it increases the rate of two things mixing or dissolving. And the reason for that is because the motion of stirring brings fresh solvent, which would be like, in this case, in this picture right here, would be like the whipping cream, or in most cases the solvent's water, into contact with undissolved solid. And in this case, it would be like the chocolate. Okay? So we agitate this so that the chocolate can come into fresh contact with whatever that other stuff is, okay, the white stuff. Or in water, like if you want to dissolve, say, some iced tea mix into water, you want to stir it around, because what you're doing is you're bringing fresh water into contact with undissolved iced tea mix. So agitation increases the rate of dissolving. If you don't want something to dissolve very quickly, you don't want to stir it. Okay. Now the last one is particle size. So if you break something up, okay, the smaller the pieces, the faster it will dissolve. That's why when you buy things like Jell-O and iced tea mix, or any kind of powdered drinks, when you get something in a powder, they're trying to get that thing dissolved really, really quickly. That's why they give it to you in a powder. They could have given it to you as a solid brick, but they don't, because that would actually really slow down dissolving. So the smaller the pieces, the faster it will dissolve. So if you're looking at, say, an ice cube, one large ice cube will not cool down a liquid as fast as crushing that ice cube up into a whole bunch of little small pieces. Now, this one will last longer. The big one will last longer, but this one will cool down that liquid as fast as possible. Okay, so if you want it to go really, really fast, but not last as long, then you're going to go with the crushed ice. And if you want to, say, go really, really slow, it doesn't really cool down the liquid very fast, but it will last a long time, then you want to go with one big block. Okay? And that's why they choose different things. Sometimes, if you're looking at, say, even like a good example is, say, a fast food restaurant, they use a lot of very smaller ice cubes. They use like kind of thinner ice cubes, because the pop that comes out, they don't want to spend the money on cooling the pop, so it's only slightly chilled. So if you ever get, say, a pop at a fast food place and ask for no ice, you'll notice that it's not really that cold. And the reason for that is they use ice to cool it down. And they use really, really thin ice cubes, much thinner than the ones that you would have at home. And the reason for that is they're trying to cool down their liquids rapidly. Okay, so if we want to dissolve ice into a liquid, so say you want to cool down your warm pop as fast as possible. Okay, say you want to cool this down super, super fast. Well, one thing that you're not going to be able to do is temperature. Okay, you're not going to heat up the pop, because it would dissolve the ice faster, but we don't really want that. We want that temperature to drop, so really temperature is not going to be a factor here. But one thing you would want to do is you'd want to stir. Okay, if you use your straw and stir your ice cubes around, it would would cool down your drink a lot faster, because stirring will cause your drink, the ice cubes, to come in contact with fresh pop, so it would cool it down much faster. The other thing you'd want to use is you'd want to use very small ice cubes, like the example that I used before with the fast food places. So you'd want to really kind of stir that around. Even better would be snow. Okay, like snow would actually be the fastest because it's almost like a powdered form of ice. But as much as you could crush that ice up, that would be the fastest way to cool that drink down. Okay, and that's kind of using all three factors. Okay, so now that we understand what factors affect dissolving, and what we kind of just went over is more of an engineering thing. So if you're really kind of enjoying well, this is kind of interesting, this is chemical engineering. Okay, it's kind of applying our processes to real life scenarios, like designing of tills or designing of products. Okay, but we're also going to talk about, well, why does this happen? Okay, because engineering only works if the science understands why it's happening. So we're going to have to kind of go through the science. Now this is kind of the why something happens, which is not really applicable to the C route, because C route's more engineering. Okay, it's more applicable stuff. It's more applying your skills, and that's why we call it an applied program, is because you're actually applying the program. But for the you kids in the class, we're going to have to go ahead and go through the science of it, which is kind of the background knowledge, where it's not really applying it. It's more, well, why does it work? So this is really for the U's. C's, you're welcome to listen through the rest of the lecture, but this is more focused on the U's. Okay, so what is happening when salt dissolves in water? So salt would be the solute and water would be the solvent. Well, what is actually happening is the forces between the particles in the solid. So these forces right here that are holding the sodium and the chlorine together, okay, they got to be broken. You have to break all those forces apart, those ionic forces. So sodium must break free of chlorine. In a non-ionic compound, like say glucose, you're not going to actually break the molecule apart, even though that's not really called the molecule. What you're going to actually do is just break the forces holding two molecules together. You won't actually separate out the molecule. You're not going to break carbon from hydrogen. You're going to basically just separate out the dipole-dipole attractions between these molecules. Okay, and that's why they dissolve pretty easily. Now, once that happens, some forces between the particles in the liquid must also got to be broken. So then you have to go in, once I break up kind of what I highlighted here in yellow, the NaCl, the next thing I have to do is I have to actually break up the waters, because they're all going to be connected together. But I want them to disconnect with each other and now start connecting to the NaCl. So I broke up the NaCl, now I've got to break up the water molecules. And then the last thing is the attraction between the solid particles and liquid particles. Since water has dipoles, okay, slightly positive, slightly negatives, and the chlorine and the sodium are ions, they're going to basically be attracted together. And notice the difference of the orientation. Okay, sodium down here, and I'm going to highlight this in green. If you look at sodium down here, it's positively charged, and it's going to be attracted to all the oxygens, which are going to be partially negative because it's a polar molecule. Then if we look over here at the chlorine's got a negative ion, and it's going to be attracted to all the hydrogens on the water because hydrogen has a slightly positive charge. And that's what's really kind of causing it to dissolve, is now you're keeping these two particles separate. And if the sodium's not bonded to the chlorine, you don't see it as an ionic compound, you don't see it as a crystal. You see it as basically an ion that's disappeared or dissolved in water. Now, if we boil all this water off, and if you say take salt water and you boil all the water off, there's nothing to keep the sodium and chloride back separate. They will reform together, and you'll see salt at the bottom. Right, and this is kind of a picture of it happening right here. Here's our sodium chloride. The water molecules are coming in and basically ripping off different ions. Okay, so that's it for the lecture. Okay, so we've followed up with a learning check, and we're in the home stretch, guys.